Hello everyone, this is Dr. Salman Zafar welcoming you to another video lecture on stereochemistry, and today we will discuss geometrical isomerism. Geometrical isomerism is a type of configurational isomerism that is characterized by the restricted rotation about a carbon-carbon double bond. First, you have to understand the difference between configurational isomerism and conformational isomerism that I have discussed earlier in another video. A link you can find here for the videos or lectures on the conformational isomerism of different types of molecules. The difference between conformation and configuration is that conformation is a low energy process which does not require bond breaking or bond formation, but in configurational isomerism, to convert one isomer into another, you need to break a bond. And we have already seen in our previous videos, which you can find here, that configurational isomerism is of two types. One we call the geometrical isomerism and the other is optical isomerism, which we will discuss later on. Today we will be discussing geometrical isomerism. Now, because it involves restricted rotation around a carbon-carbon double bond, so it means that it is exhibited by alkenes, which have a carbon-carbon double bond in its structure. Geometrical isomers are defined or expressed with different notations. So you can express them with cis or trans notations, or you can express them with E and Z notation. We will discuss each of them separately in a couple of moments. So let's see what cis and trans isomers mean. So we have this molecule ethene, which has two carbon atoms joined together through a carbon-carbon double bond, and each of the carbon atoms have two hydrogens attached to them. Now, this molecule cannot have another isomer, so we cannot have cis or trans isomers for this molecule. Similarly, if we have another molecule like propene, this molecule has two carbons double bonded to each other. One of the carbon atoms has two hydrogens and the other has a hydrogen and a CH3 group attached to it. Again, we cannot have cis or trans isomers for this molecule. Now, where can we have cis or trans isomers, or what is meant by cis or trans isomerism? So we have as an example 2-butene here. Now, if you look at these two molecules, both of them are 2-butene, but if you look at the structure closely, they're different from each other. If you see here, we have a carbon-carbon double bond. This carbon has a CH3 here, a hydrogen here. This carbon has a CH3 here and a hydrogen atom here. Similarly, this molecule has a carbon-carbon double bond, a hydrogen here, a CH3 here, a CH3 here, and a hydrogen here. Now, it's just the difference of the relative orientation of these CH3 or hydrogen atoms that make these two molecules different from each other. Their molecular formula is the same. Both have 4 carbon atoms and 8 hydrogens. But if you look at their structural formula, they have different orientation of these two groups. Right? So if you take this carbon-carbon double bond, a plane about this carbon-carbon double bond, you see that these two methyl groups are on the same side of this carbon-carbon double bond, and the two hydrogens are on the same side of the carbon-carbon double bond. But here you can see that these two CH3 groups are on opposite sides of the carbon-carbon double bond, or the two hydrogens are on opposite sides of the carbon-carbon double bond. So it's just the orientation of these CH3 groups or the hydrogens that make these two molecules different from each other and make them isomers of each other, which we call the geometrical isomers. Now let's see, if you want to convert this isomer into this one, you just have to rotate this carbon atom around this carbon-carbon double bond. So this CH3 comes down, H goes up, and then you can have this isomer. Or you rotate this carbon atom through this carbon-carbon double bond, so CH3 goes down and H goes up to give you this isomer. But as you know that rotation around this carbon-carbon double bond is restricted. So rotation is not possible at room temperature. You have to provide energy to make this possible. And during that process, when you provide energy, one of these two bonds, the pi bond, which is weaker of the two, is broken, and we are left behind with a sigma bond, a single bond around which rotation is easier. So the groups rotate, and then the pi bond is formed again. So that is why we say that configurational isomerism or configurational isomers are not interconvertible at room temperature. You have to provide them energy, and that is why it's a higher energy process as compared to conformation. Now let's see what type of isomers these two are. So we call this molecule as the cis-2-butene and this one as the trans-2-butene. Why? Because here we have these two CH3 groups on the same side of the carbon-carbon double bond. So if you have two similar groups on same side of the carbon-carbon double bond, which is true for the CH3 as well as for the hydrogen atoms, then we say they are cis to each other, and the complete name is cis-2-butene. Here again you see that these CH3 groups are on opposite sides of the carbon-carbon double bond. So when similar groups are on opposite sides, we say they are trans to each other, and the name of this molecule is trans-2-butene. So this is the trans isomer of 2-butene, and this one is the cis isomer of 2-butene. Cis and trans isomers can also be present in cyclic molecules, which I have discussed in another video. You can find the link here. In case of cyclohexane, substituted cyclohexane can have groups on the similar side of the ring or on opposite sides of the ring. So molecules or rings having groups on the same side are said to be cis cyclohexanes, cis disubstituted cyclohexane or trans disubstituted cyclohexane, that I have discussed earlier in another video about the conformational isomerism of substituted cyclohexane. But here we are talking about geometrical isomerism. So this is how you can differentiate between cis and trans isomers. So it's quite simple. Now let's see how these cis or trans isomers differ from each other. So cis isomers have relatively higher boiling point as compared to the trans isomer. This is because of the different polarities of the cis or trans isomer. Cis isomer is has a relatively higher polarity as compared to that of the trans isomer, because as you saw in the previous example, the CH3 groups were on the same side, so the dipole moment is enhancing the same for the CH3 group, so it is being enhanced, and so the dipole moment is higher, the polarity is higher, and that is why the dipole-dipole interactions are higher, which makes it harder for the cis isomer of any molecule to boil. So that is why the cis isomers have a higher boiling point as compared to that of the trans isomer, which have groups on opposite sides, so the dipole moments cancel out, and that is why they have a lower boiling point, lower dipole-dipole interactions, and easier for the molecules to get separated, and that is why they have a lower boiling point. Interestingly, cis isomers have a lower melting point as compared to the trans isomer. Now melting point is more or less related to the symmetry of the molecule, and as you can see that the trans isomer is more symmetrical as compared to that of the cis isomer. Cis isomer having these groups on the same side, so it's less symmetrical as compared to that of the trans isomer, and melting point is related more to the packing of the molecules. So the trans isomer is packed more efficiently as compared to the cis isomer, and that is why when they are packed together, the interactions are higher and it is harder to separate them or convert them into liquid form. So that is why the trans isomer have a higher melting point as compared to that of the cis isomer. And as I told you earlier, because of the orientation of the groups on the same side, they are more polar as compared to the trans isomer. Similarly, cis isomers are highly soluble in inert solvents as compared to that of the trans isomers, again because of the different polarities, and they are also more acidic as compared to the trans isomer. And you can see as an example the malic acid and fumaric acid, which have different pKa values. Another type of notation that you can use for defining or differentiating between geometrical isomers is the E and Z notation. Now let's see what E and Z notation means, or how you can differentiate between them. So E is from a German word Engen, or you can pronounce it in a different way, which means opposite, and Z is from zusammen, which means together. So both are German words which mean opposite and together, and that would mean that in Z isomer the groups would be together or on the same side, and in E isomer they would be on opposite side. Now which groups are we going to see and decide whether they are on the same side or on opposite side? That is through some assignments made according to CIP rules. CIP rules mean the Kahn-Ingold Prelog rules assign different priorities to these groups across the double bond, and then later we decide whether they are on the same side of the carbon-carbon double bond or on opposite sides. So according to the Kahn-Ingold Prelog rules, the atoms attached to each of the sp2 carbon atom are ranked according to their atomic numbers. So the atom attached to the sp2 carbon having higher atomic number will have a higher priority, and another atom attached to the same sp2 carbon having lower atomic number will have a lower priority. And then we see whether the higher priority groups are on the same side or on the opposite side. So if the higher priority groups are on the same side, we say that it is a Z isomer, and if the higher priority groups are on opposite sides of the carbon-carbon double bond, then it is an E isomer. So let's see this with the help of an example. Again, we have a 2-butene. We have already seen that this is a cis 2-butene, but let's see if it is E or Z. So for this purpose, we have to analyze each of these sp2 carbons separately. So first we check the groups attached on this carbon atom, this sp2 carbon. So this carbon has a carbon atom and a hydrogen atom attached to it. Now, one thing you have to remember is that you don't have to look at this group as a whole. Like, you cannot say this carbon has a CH3 group, but in fact you have to proceed atom by atom. So you have to check the first or the directly attached atom to this sp2 carbon on both sides, and then you proceed further. So we have a carbon atom here attached to this carbon, and here we have a hydrogen atom. Forget about these 3 hydrogens for the moment. Now you decide which one of these two have a higher atomic number. So carbon of course has a higher atomic number. So CH3 has a higher priority as compared to the hydrogen. Now we analyze this carbon atom, and this carbon sp2 carbon again has a carbon atom and a hydrogen attached to it. Carbon having higher atomic number will be ranked higher as compared to the hydrogen atom. So now we have ranked or assigned priorities to all the groups attached to both the sp2 carbon atoms, and now we see the higher priority groups, whether they are on the same side of this carbon-carbon double bond or on opposite sides. So in this case, the higher priority groups, both of the higher priority groups are on the same side of the carbon-carbon double bond. That is why the geometry is Z in this case. So this is a Z2-butene. Now we have another example here. This is a trans 2-butene. So let's see if it is E or Z again. So first we analyze this carbon, which has a hydrogen and a carbon again attached to it. Carbon having higher atomic number is ranked higher as compared to the hydrogen. And on the other side of the carbon-carbon double bond, we have a carbon and a hydrogen again. So carbon again has a higher priority as compared to hydrogen. And now you see that the higher priority groups are on opposite sides of the carbon-carbon double bond. So in this case, the geometry is E. So this is E2-butene. Now this EZ notation is helpful when you have different groups attached to the sp2 hybridized carbon atoms. In that case, you cannot assign cis or trans isomerism. Here, of course, this is quite simple. You can assign cis or trans geometry as well. But in molecules having different groups attached to both the carbon atoms, then it is easier to assign E or Z notation to these molecules. Now you may have molecules in which an sp2 carbon has two similar atoms attached, like an sp2 carbon has two carbon atoms attached, or oxygen attached, or nitrogens attached. Then how will you decide the priorities? So if the first or the directly attached atoms are similar, then you see the atom next to this directly attached atom, and then you decide the priority. If the second atom is also similar, then you move further and check the third atom. If that is similar, you move to the fourth atom, and so on until you reach the first point of difference. And that is where you will decide priorities or the higher or lower rank of a group attached to that sp2 carbon. So as an example, we have this molecule here. So we analyze this sp2 carbon, and you see here it has a carbon atom attached here, and it has a carbon atom attached here as well. And now we have similar atoms having similar atomic number, so we cannot rank them or we cannot assign priorities here. So to assign priorities, we have to check the next atom that is attached to these two carbon atoms, right? So this carbon has three hydrogens attached directly to it, and this carbon has two hydrogens and one carbon attached to it. Now these two hydrogens have similar atomic numbers or priorities to two of the hydrogens attached to this carbon here. Now here we are left with one hydrogen, but here we do not have a third hydrogen. In fact, we have a carbon. So carbon has a higher atomic number, so this group will have a higher priority as compared to the CH3 group. So you proceed atom by atom to assign priorities to the groups attached. And on the right hand side, it is obvious we have a carbon and a hydrogen, so you can assign priorities easily. And now you see that the higher priority groups are on opposite sides of the carbon-carbon double bond. So this molecule has an E geometry. Let's see another example. Now in this molecule, this sp2 carbon has oxygen attached on both sides. And because they are similar, they have similar atomic number, we cannot assign priority because of the oxygen. So we move on to the atom attached to this oxygen. So here we have a hydrogen as the second atom, and here we have a carbon as the second atom. So carbon having higher atomic number as compared to hydrogen will have a higher priority, and OH will have a lower priority. And on the right hand side, carbon has a higher priority as compared to hydrogen. So again, the higher priority groups are on opposite sides. That is why it is an E isomer of the molecule. Now you may find some atoms which are multiply bonded to an sp2 atom, carbon atom, or the atom next to it. In that case, that multiply bonded atom is considered as being attached twice to that atom. So as an example, we'll see this molecule. Here you have a carbon-carbon double bond. This sp2 carbon has a carbonyl group attached to it here, and we have a CH2OH group attached here. Now this molecule can be considered as being this molecule. Because we have a carbon atom directly attached to this carbon here, and we have a carbon here as well, so these two carbons cannot decide the priorities of the group. So we have to check the atoms that are attached to these two carbon atoms. So for that purpose, we see here this carbon atom has an oxygen that is double bonded to this carbon atom. So a double bonded or a multiply bonded atom is considered as being attached twice. So this can be considered, just for the sake of assigning priorities, as this. So it means that this carbon actually has two oxygens attached to it. It's not true structurally, but for the sake of assigning priorities, we consider this oxygen as being attached twice to this carbon atom. So let's assign priorities now. So we have a carbon here, a carbon here. We cannot assign priorities here. So the atoms next to this carbon are oxygen, oxygen, and carbon. And the atoms next to this carbon are oxygen, hydrogen, hydrogen. And so you see that this carbon atom has two oxygens, this carbon atom has one oxygen, and that is why this group will have a higher priority as compared to the CH2OH. And on the right hand side, again, we have a carbon and a hydrogen, so you can assign priorities easily. And now we have higher priority groups on the same side of the carbon-carbon double bond. So this molecule has a Z geometry. Let's see some other examples. So we have this carbon-carbon double bond, which is tri-substituted. So we have a methyl here, and a chlorine atom here. So on the left hand side, we have a chlorine and a hydrogen. Chlorine having higher priority, of course, is ranked higher. On the right hand side, we have a CH3 and hydrogen. So the carbon atom has a higher atomic number, so it will be ranked higher. So the higher priority groups are on opposite sides, and that is why the geometry is E. In this molecule, we have on this sp2 carbon, a carbon atom and an oxygen. So oxygen obviously will be ranked higher. On the right hand side, we have a carbon and a chlorine. So chlorine has a higher priority, and so the higher priority groups are on the same side. The geometry would be Z. Now this molecule, we have a carbonyl group again and an OH group. So you just see the first atom, which is a carbon here and an oxygen here. So oxygen will have a higher priority, and on the right hand side, comparing carbon and hydrogen, carbon will have a higher priority. And now you see the higher priority groups are on opposite sides. So this is E isomer. Here we have a bromine and chlorine attached to this carbon. So bromine has a higher priority, and on the right hand side we have some groups attached. So we have a carbon here, a carbon here as well. So carbons cannot decide the priority, so we check the atoms that are directly attached. So this carbon has a hydrogen, this carbon also has a hydrogen. So again, we cannot decide the priority. This carbon has another hydrogen, but this carbon has a carbon here. So this carbon has two hydrogens and one carbon attached, while this carbon has one hydrogen and two carbons attached to it. So this group will have a higher priority, and so the higher priority groups being on opposite sides, the geometry would be E. Again, we have a bromine and chlorine, so bromine has a higher priority. On the right hand side, we have a CH2OH and this butyl group attached, in which a carbon atom has three methyl groups attached to it. Now you see here we have two hydrogen and one oxygen attached. Here we have three carbons attached. So carbon attached to oxygen here, and a carbon attached to carbon here. So this will have a higher priority, and the geometry would be Z. Here we have again a bromine and chlorine. So bromine has a higher priority, and on the right hand side we have a carbon that has a double bonded carbon to it, and here we have again a carbon atom with 3 CH3 groups attached to it. Now this carbon atom has one hydrogen and 2 carbons, because this is a multiply bonded carbon atom here, so it will be considered as being attached twice. So this carbon atom will have 1 hydrogen and 2 carbons, but this carbon does not have a hydrogen. In fact, it has 3 carbons attached to it. So again, this will have a higher priority, so the geometry would be E in this case. So this is how you can assign geometrical isomerism or cis-trans or easy notations to alkenes. I hope it helps. Thank you so much for watching. Stay tuned for some more lectures in stereochemistry coming up. Thank you so much.